So this is just a continuation or follow-up to the first webinar, which we did in September, where we looked at different scales, introduced a little bit on sample prep. Also, we looked at different limitations, advantages of different scales. What I would also suggest is if you missed the first session, you can always go onto our website and you can click a recording of the first webinar session. So just hang on a second. I'll wait for maybe 1 or 2 more minutes before I start or kickstart the webinar session. And thanks again for joining us. I know you've taken time from your busy schedules, but hopefully after this we will have shown you something slightly new, slightly different, or something that you haven't done or might be doing going forward. So I think I can start the session. And I'll start the session by doing a quick poll. And the poll is I just want to see or gauge if you all can hear me. So if you can click on there, if I'm audible enough, if you can see my screen, and sometimes it might be a case of just adjusting your system to make sure everything is looking okay. Okay, so I can see nearly 100% guys, you can hear me and see the slides. Okay, thanks for the poll. So if I start off the webinar, this is, like I mentioned before, is the second or follow-up to the first webinar where we looked at different scales and how they're specified. We did talk about advantages and limitations for different scales used in hardness testing. We also looked at the depth, sample preparation requirements, and how that correlates to accuracy of measurement of hardness testing. In this webinar today, I'll be talking about heat treatment evaluation and how we do that for hardness testing. I will take you through fracture toughness of brittle materials, talk a little bit more on how we evaluate welds, either following the 9015 standards, or you may have your own in-house way of testing welds. I will cover hardness mapping and its advantages in terms of being able to visualize hard surfaces compared to soft regions, as well as it's a qualitative way of gauging residual stresses in your material. I'll finish off by talking about direct and indirect verification of machines. And we do this to ensure that whatever you're getting as your test data is accurate and you've got high confidence level on what you're looking at. So as an overview from the first webinar session, we looked at Brinell scale, where we're using ball indenters. And once you've done an impression, you use an optical system to read that impression. And for Brinell scale, loads can be upwards of 3 tons. But the main one, the key point to take from Brinell scale is always to ensure that the D, which is the diameter of the impression, compared to the diameter of the ball, meets certain criteria to get accurate reading. And this is typically between 0.26 to 0.6. So if you're not meeting this, then you may not get accurate results from your Brinell testing. The other component that we also mentioned last time was F over D, which is the force applied compared to the diameter of the ball that you're using. And for Brinell, we said it's comparable in terms of Brinell value. So if you're working for HP 30, for example, you can use a 3-ton load with a 10mm ball. That should be equivalent to using a 750 kilogram force with a 5mm ball. We also talked about Rockwell scale, which is an indentation depth-based technique, so no need for optical reading, which just minimizes measurement errors related to optical reading. The only other side of Rockwell that you have up to about 30 different scales available. And within these scales, you may need to use different indenters, be it ball or conical-shaped indenters. So that brings a little bit of complexity. But the advantage is because it's an indentation depth-based technique, it does give you a very good understanding of how hard your material is. A common technique is Vickers scale, and in this case, we're using a pyramid-shaped indenter. And what we're doing essentially is reading the diagonals to get D1, D values, which is plugged into an equation to give you your Vickers value. The advantage you've got with Vickers scale is one indenter fits to most application. And another advantage is when you're working with low load testing, for example, using 25 or 50 grams, you can analyze small areas within your material, or even if you want to analyze different phases within a material, for instance. The other technique we also looked last time was NOPE scale, which uses an elongated rhombohedral indenter. And with the NOPE, you don't get more of the depth being impressed onto your surface. So it's more of a surface technique, which means you typically use really low test forces. And it's also ideal for brittle materials or whenever you're working with thin film systems. Also, as a continuation, we looked at preparation requirements and measurement effects and how these correlate to hardness testing. And all in all, the message to take from here is that a high degree of surface finish will always give you more accurate and reproducible results. And for instance, if you're working with Brinell, a ground surface to P400 might be more than sufficient to be able to read your ball impression. But also, you need to remember, depending on which ball impression, if you're using a 1 millimeter or 2.5 millimeter diameter ball, it may necessitate that you prepare the surface a little bit better. For Rockwell, again, this depends on the load that you're using, but you're saying that a fine-grained surface is often more acceptable even at high loads. For macro Vickers, where you're using 5 kilos and above, then we're also saying that a fine-grained surface is often more acceptable. But we do recommend that, if possible, polish the surface to get better accuracy. Superficial Rockwell, where we're using low test forces if you compare to most scales in Rockwell, we're saying that if you can prepare a surface to a 3-micron finish, should be ideal to give you good results. And last but not least, when you're working with micro hardness, be it Vickers or NOPE, we recommend that you prepare a sample to a final polish of less than a micron. And I'll show you why that is the case. So this is a typical charts illustrating. The one onto your left illustrates different load levels and how that correlates to different surface finish and the expected hardness value that you'll be able to get from that measurement. So if you look at HV10, which is 10 kilo, more in the macro scale, the component we are testing here is about 475 Vickers. So you can see at HV10, it's close to where we need to be. And this is for sample preparation where you've done a P320, P600, 180. It's quite close because it's a big impression. You do get more of an accurate reading of your impression. But as we go down on the test loads, down to 300 or 100 grams, you can see the dispersion is a little bit more. And that's why when I said always having a polished surface is the deal, for as long as you're within this window, you are within what we call allowable tolerances. So you may be a couple of points up and above. And as I will illustrate again, going back to 10 kilo, if you're working with 10 kilos, for instance, if you ground that surface using P80, for instance, and try to do impression, because you traditionally think it's macro Vickers, you can see you've got close to 150 Vickers points between accurate reading vis-a-vis reading attributed to sample prep. Also, last time we also mentioned about measurement variability from low to high load in micro Vickers range. So when using a test force, for example, 1 kilo, you do get minimal dispersion. This is a case of different labs looking at the same material, same impression, and then we're trying to evaluate how well they get the measurements or correlate to where it should be ideal. So in this case, you're seeing a sample, for example, which is at 700 vickers, about 725 or 750 vickers, another one about 450, another one at 250 vickers. So for the low vickers levels, you get good correlation, but also you see when you're doing low force, say 50 grams, 25 grams, there's a little bit of dispersion. This is more highly magnified when you're looking at 700 vickers level, and you can see the bell-shaped dispersion is quite high. And so what we're saying from this chart is you can minimize some of these issues by first always ensuring you've got good sample preparation procedures in place. And better still, if you can have a way of your machine having a level of automation for focusing, as well as being able to measure the impression that you've done on your surface or sample. So I'm going to do another quick poll. So I'm not talking only to my computer. And in this case, I just want to have a feel of what kind of equipment to use for your hardness testing. So this can either be you're using Brinell tester, Rockwell, or Vickers and or Noob tester. Universal hardness testing is where you've got a machine that can do both Rockwell, Vickers, and the Brinell as well. And I can see interesting polling, so I'm just going to give it a couple more seconds so you guys can do the poll. So predominantly it's Vickers and Noob testing, you can see, and I will share the results after the vote. But it's interesting that guys are also doing using the portable testers. For example, when you're using dynamic testing, using a lib or ultrasonic contact impedance tester for hardness checks. So I'll close the poll, and then I can quickly share the results of the poll. Just give me a second. So as I explained before, so this is what you've polled. Nearly 90% I've got predominantly Vickers and Noob testing, followed by Rockwell, Brinell a little bit. But it's interesting to see also that portable testers are also being used at your places. Thank you for doing the poll, and then we'll go back to our webinar. So for the first application I'll be talking to you today about is looking at heat treatment evaluation. And in this case, I've classed this to look at substrate treatment processes. And this can either be either through a selective process or a diffusion process. And why we do this, of course, we want to obtain high surface hardness for an area of interest that we want to harden. And by doing so, we do increase the wear resistance and anti-scaling properties for melting surfaces, for instance. We want to improve fatigue life of components which have been heat treated. Again, depending on the species that have been used to heat treat the surface, you may have good intermetallic forming on the surface that can also aid in corrosion resistance. And ultimately, of course, if you think about a crankshaft along the crank journals, which are typically induction hardened, you can have a surface that is resistant to softening at elevated temperature. So if I go into some of the typical processes, as an example for selective, when we're looking at induction hardening, in this case, you've got your sample, which is heated through induction. Parts definitely have to be conductive. And then after heating up your component to a temperature of interest, you quickly quench it, you freeze the microstructure, and with induction hardening, the advantage you've got is you do create deeper case depths, and the process time, of course, is from a couple of seconds to minutes. The next technique is nitriding or nitrocarburizing, which is a diffusion kind of substrate treatment process. And in this case, you're using either gas, be it ammonia, or salt bath, which are nickel-rich salt, or you can also use ionized nitrogen. And in this, essentially, we're impinging nitrogen into the surface, creating a harder region. And with nitriding or nitrocarburizing, you do tend to cause shallow case depth, and the process time can take a couple of hours to get the right case depth. The other technique is carburizing. which is also classified as a diffusion process. And this can either be done through gas when you're using plasma or vacuum carburizing, or it can also be salt paths, or you can use pack cementation, for example. And in this case, we are diffusing carbon into the surface at temperature into solid solution in austenitic phase, and then you quickly quench that or cool that down to freeze the microstructure to get the harder case. And for carburizing, you do tend to get medium case depth, and the process time can take up to hours as well. So which heat treatment should you essentially choose? We're saying here that the preferred hardening process, of course, depends on a number of factors, one of them being process time, which I've alluded to in the previous slide. But we're also checking that the case depth capability, as you can see on the schematic on your right on that chart, nitriding tend to cause shallow case depth, followed by carburizing, which is we say does cause medium case depth, and then you've got induction hardening where you can get a lot more case depth capability. But also the technique can also be used to volume harden components if you want a through hardened component. We're also saying another factor that you need to take into account is what post-treatment might be required. You may need to machine a component down to desired tolerances. So whichever technique you're going to use, you need to make sure that you still have your case depth and it is serving the purpose you've put that case there for. Also, temperature range, this is correlated to the material type that you're trying to heat treat. Cost implications, of course, different techniques cost differently. For the nitriding or carburizing might be a little bit more on the costly side compared to induction or flame hardened components. Again, just to reiterate, the maximum hardness achievable is something that you've got to take into account, but that also has a correlated to the depth to which you can get that core surface hardened area. So sometimes used and how those correlate to hardness testing. We do have what we call case hardening depth, and typical loads in this case is from 100 grams up to a kilo or even 5 kilos. And in this case, we're evaluating the hardness at 550 vehicles, or approximately 50 to 52 Rockwell value. And essentially, the case depth is the distance from the surface to point where the hardness hits 550 vehicles, as schematically shown on that chart. For induction of flame hardened parts, in this case, you can either use traditionally where you're going with 550 vehicles, or you can also base your case depth at 80% minimum of your surface hardness. And essentially, the distance from the surface to point where your hardness is 80% of that surface hardness is what you consider as your case depth, as illustrated there. And as you can see in this case, for when you're using 80%, it's slightly above the 550 value, but pretty much close. So that's what I'm saying. Depending on how you've specified your tolerances in your production, you can use either of the techniques. For nitrided parts or nitriding hardening depth, in this case, we're basing that limit or the distance from the surface to point where the hardness is 50 vehicles above the core hardness. So as illustrated there, you can see the core hardness value there, the little red point. And we're basing this case depth on 50% plus this level. But again, depending on the material that you're hardening, this tolerance or the plus value can either be 50, 100, or 150 vehicles. And it's just show you different ways we can do hardness check or case hardening depth analysis. So I'm going to give you a typical example of a hardened shaft, and this we're looking at a drive shaft. This has been sectioned as illustrated there with the red dotted lines. And after sectioning, we've ground the surface, polished, and etched it. So when we etch the surface, it is easy to see where the induction hardened region is and where the core regions are within the component. Also, we are evaluating here the surface hardening depth at 550 vehicles using 1 kilo as the load. And this illustrates an image where we've done a stitched up or mosaic of that component. And sometimes if you've got a system that can really scan your samples, it just gives you a lot more versatility on how many first what we call locations that you can test to just validate that your component is okay. So this is a stitch-up image taken from the hardness testing. And what you're trying to do is you clearly see for an edge surface, you can see the transition from the induction hardened bit, which is that region I'm highlighting there with the cursor. And then the red point highlighted there is the transition from the hardened surface onto the core material. And typical profiles that you'd get during hardness testing, this is an illustration at 550 Vickers, and we got a case depth of this about 3.097 millimeter from the surface. So how does this relate? I mean, you can also use the 550, the 80% minimum surface hardness, but then we can look at the microstructure, the way of seeing if we've done proper induction hardening. And in this case, if I blow up that surface where I'm looking at, you can see the transition from your core surface, which is predominantly characteristics of ferritic and pyelitic region, into the hardened component, which is predominantly or should be a matensitic microstructure. If we go high magnification, and that's the typical microstructure, for example, for this component that you would expect to see. On your right is the matensitic microstructure, which is desirable, gives you high hardness. And the pyelitic or ferritic, which is the core, is a little bit pliable, so improves a bit toughness on that component. The next is application I'll be talking to you is looking at a nitrided sample, in this case a valve guide. And in this case, we've sectioned through as indicated by that dotted line, and we're evaluating the nitride hardness depth at core value plus 50 Vickers. And this just illustrates a typical indents done on that component from the surface into the core of the valve guide. And in this case, we used 50 grams because when we etched the surface, as I'll show you in the next slide, we realized that the nitrided region is quite thin. So we've just used low test force, which also means that the surface preparation has to be really good to be able to accurately measure the impressions. And as you can see there, the core hardness value, which is 243 Vickers, and we based the case depth at 50 Vickers plus. So that transition gives you an indication of where your case depth should be. And this is just another blow-up image of that actual sample. And you can see with the micron marker showing about 200 microns. So from the surface onto the core area, it's just short of 300 microns. And this is why we used a low test force to be able to accurately gauge the nitriding hardness depth for this material. Sometimes when you etch the surface, like I mentioned before, that's why you're able to see the different surfaces where I would say you've got the compound zone, which is the visible outer bit, or what traditionally is considered as a white zone, white layer. And then the dark region is the compound zone or the fission zone, which is where you've impinged or added a lot of nitrogen to surface harden that or create a case for this material. So there are impressions there that might not be readily visible. And this is just a blow-up image, again, to show you the white layer and the respective microstructure in as etched situation. We've also just included a dark field image to illustrate where the impressions are. And this is why I was mentioning before, sometimes for these kind of surfaces, you may need to do the testing before etching, because all hardness testing, most of the time, they do use contrast technique to accurately measure your impression. The next one I'll be looking at is a carburized component. In this case, we are looking at the gear tooth, for instance, and we're evaluating the case depth at 550 Vickers using HP1 or 1 kilo. And this illustrates where we've done multiple locations around the tooth to give you an indication of how well you've carburized that component and ensuring that you've got your case depth at where you've put it as your tolerance level. And as you can see from the chart there, that's a really good match of where the case depth should be. Another advantage that you can do, as you can see, we've got a little bit of a heat map where we've taken the same tooth and did hardness mapping on it to highlight the harder surface. So from the heat map, the hard regions, we are looking above 650. And then as you come to the core, is a little bit softer, looking about 400 Vickers level. And this is typical microstructure for a carburized component, starting from a really hard surface and going into the core where it's a little bit softer. I'm gonna do another quick poll again, so that you guys don't fall asleep for me. And in this case, I know I've already highlighted some of the applications that I'll be talking about, but it's just to have a feel of which kind of hardness testing in terms of application-wise you carry out. So if you can quickly do a poll for me, whether you're doing routine surface or core hardness checks, or if you're doing CHD, NHD, or SHD evaluation, weld evaluation, hardness mapping, and KIC, or indentation fracture toughness measurement. Okay, so I'm going to give it a couple of more seconds. And I see majority are doing routine surface and core hardness checks, with 50% already working on case depth evaluation. Interesting that there is also K1C or indentation fracture toughness being carried out. So I'm going to close the poll and show you the results of the poll. And I'm sorry if I've cut you off. And as you can see there, 92% are looking at routine surface and core hardness checks, followed by case depth, weld evaluation, and we've got a couple of doing hardness mapping, as well as KIC indentation fracture toughness test. So I'm going to go back to the presentation. The next application I'll be talking to you about is indentation fracture toughness, or KIC. And for fracture toughness, this is a material property that defines how well that material resists fracture. And for IFT, this is ideal for brittle solids when you're looking at things like nitrides, carbides, or common structural ceramics. And traditionally, of course, you can, before this was adopted as a technique, people tried using Vickers and NOPE, but we prefer using Vickers indentation because of the fourfold symmetry from the Vickers indenter compared to the NOPE, which I mentioned before is rhombohedral in nature. But also with Vickers, you do get deeper indentations that are more likely to fracture your material and propagate cracks at the tips of the impression that has been made on the surface. We're also saying that for Vickers, of course, it allows you to do higher test loads as opposed to NOPE, where most of the time you're pegged to 2 kilos at most. And the technique, of course, has been adopted because of the specimen geometry requirement. If you look at that standard, for example, for certain material, this may not be an easy way to do. And this is why we stick to indentation fracture toughness as a way of validating how well a material resists fracture. In terms of preparation requirements, typically we say when you're doing IFT analysis, you want to go to 1 micron finish. And this should be typically suitable to be able to analyze the cracks that develop from your impression. And something else to also take into account, you also have to ensure that whenever you're doing an indentation, the specimen is perpendicular to the specimen that you're looking at to get good crack profile. So for indentation fracture toughness, I mentioned it's ideally suited for brittle materials. And in this case, I'm giving an example for those guys working with aluminum nitride, or if you've got silicon carbide as material of choice. Other components like tungsten carbide, cobalt components, or cemented carbides, or if you're looking at silicon nitride, alumina, and other ceramics. So there are equations that have to be selected, and this selection of these equations are predominantly determined by the C/A ratio, which I will explain in the next slide. So this can either be Nihara, which is a median type of equation, We've got anstey's, again, for C over A ratio greater than 2. And when you're working with Shetty, which is less than 2, that would be ideal for that tungsten carbide cobalt component. And Miyoshi is also another equation, ideally for C over A ratio greater than 2. And the message to take from this is, of course, match the material that you're working on with a specific question to get accurate IFT results. So I did mention about the C over A ratio, and the C over A ratio, you're looking at the crack length from the tip and looking at the impression made. So this ratio is what I meant, that we need to ensure that whenever you've applied the load to make an indent, and the cracks, of course, will come from the impressions, depending on the equation that you're going to select. If it's a median type of equation, you always ensure that your C over A ratio is greater than 2. And when possible, if you can push it to 2.5, just gives you that a higher confidence level on the results of your IFT results. Or for palm-based, these equations, in this case, we're looking at C over A ratio of less than 2. But like we said, whenever you're doing some of these tests, you may not know which is the ideal load to use for your fracture toughness. And what we're saying here, or advising here, is you can't try and test different loads until you get a proper crack profile that ensures and meets that C over A ratio criteria. And as you can see on the micrographs on your right, we've got the top one, which gives you an indication of an ideal crack. And an ideal crack, remember we said it's ideal if your indent is coming onto the surface, perpendicular to that surface, to ensure you get good propagation. But sometimes if your surface is not flat, you may have cracks emanating at different location. The image at the bottom right, which is not ideal for KIC calculations. So within our software, we've developed or added this tool. And this tool allows you to do KIC measurement in a simplified manner. And in this case, when you're programming, you pick whether you're working with KIC, pick the method depending on the C over A ratio if you're working with median cracks. So that can be either Anstey's, Nihara, Laugier, or Miyoshi. And when you're working with palm-based, you can take Nihara or Shetty, put the elastic modulus of most materials are commonly known, your test load that you've used, which ensured you got the right C over A ratio, and automatically, once you do the test, you get your test output test data, which gives you the measured Vickers value at 10 kilos, your corresponding KIC value, and you've got the D1, D2, which is the diagonal length for that impression, which would be, in this case, the D1 average, D2 is an indication of your A value, and the crack length gives you how far it's propagating from the tips onto your material. And this is just a quick way of evaluating indentation fracture toughness. So we've got this incorporated into a software for those of you working on KIC measurements. The next application I'll be talking to you about is weld evaluation. Welding is typically is basically a fusion technique where you're joining two solid sections. And the technique can either be gas, arc, or resistance welding, or high energy beam where you're using lasers, for example, or solid state welding. Example is when you do ultrasonic welding or friction stir welded. And the images on your right there, the top one just shows you the gas tungsten arc welding, where you've got your filler rod coming into the weld pool, where it's been melted by the arc to fuse two components. And the image at the top, at the bottom there, which is resistance type of welding, illustrates a spot weld. And the spot weld, in this case, we've carried out electroback scatter diffraction to give us an indication of how the material behaves and the different structures that correspond to that spot weld. And like I mentioned before, welding being a highly localized melting operation, it just means that during solidification, you'll have conditions that cause rapid cooling. And this cooling is due to heat loss to the atmosphere, or it can be through thermal conduction into the welded component. So when you think about, you've got a case of localized high heat input, and you've got rapid cooling, and depending on the technique that you've used to weld your components, you will have changes in microstructure, starting from the weld into your base of parent material. There will be a heat-affected zone formed at the interface between the weld into your parent material. Pores and voids can also occur depending on the technique you've used. Predominantly find this within the weld and occasionally, of course, along near the fusion line. But also cracks can develop around the welded area after you've welded your component, what we consider or call as heat cracks, for example, reheat cracks. So what are the main factors we consider whenever we are looking at welds? And this is a schematic. The image on your top left illustrates a typical weld bed, which is at a maximum temperature when it's being welded. And as you move away from the weld bed, you do get a solid boundary, which is where you'd find your fusion line. And from there, you do have a region where you've got grain growth. And remember I said these conditions are conditions of rapid cooling. You may have a different type of microstructure, which is quite hard. And as you transition into the unaffected base material, you will see different microstructures developing. And whenever we are looking at welds, you consider welds on a welded component, whether they can be overmatched, which means the weld is stronger than your base metals, or the weld can be equally matched, which is of equal hardness compared to your base metal, or undermatched, where it is weaker than the parent or base material. The hardness profile that you typically get, which is the schematic chart illustrating on your top right. Starting from the base metal, you may have similar hardness, and as you get into the heat-affected zone, you can have a drop or an increase all the way up to the weld metal. And in this case, just illustrates when you've got conditions of a matched weld, and undermatched weld condition. So typically on a welded component, depending again whether it is over, equal, undermatched, you'll have high hardness within the weld. And also the heat-affected zone will always have high hardness and gradually decreasing to below the parent metal. And what we say for weld, typically you'd take it through a post-weld heat treatment, and that serves to reduce the hardness and scatter in the weld metal and the heat-affected zone. So how does this all tie in for ISO 9015 for weld evaluation? The procedure gives you how you're going to place your indentations on your material. And in this case, we're looking at if you're doing rows of indentations, it does specify how many you're going to do, how they're going to space out. And the key here is to ensure that you define the hardened and softened regions correctly, and you're also covering the parent and base metal. And it also does specify that for metals that do harden in the heat-affected zone, you may need to add 2 additional indents to properly evaluate that welded component. And whenever you're carrying individual indentations, we're saying that the location of indentation can be determined through metallographic examination. You etch the samples, give you an indication of where your base metal is, your heat-affected zone, and your core region, and you can individually place this indentation. But you also have to remember to adhere the distance between indents have to be 2.5 times the D1, D2 average for the impression that you've made. And of course, it's always advisable for the areas tested to be numbered where you've done your indentations. So as typical example, which is specified in this standard, in this case, we're looking at a butt welded component, and it does specify you need to do 3 indents in the parent metal, 3 additional indents within the heat-affected zone, and as I mentioned before, for metals that tend to harden in the hards, you can add 2 indentations on either side as illustrated there. And the standard does specify how well they should also be spaced out. And also into the weld, you need to do 3 additional indents. When you look another example of a fillet weld, just with a single bead, it does also indicate or show you how you should place your indentation to properly evaluate that surface. And if you can think about this, or when you're working with butt welded component, if you're individually doing individual indentations without really knowing where you're placing this, it can be an arduous task. I have done this previously in my role where I was in oil and gas and assessing quite a lot of welds. It can be a challenging and time-consuming analysis to do. But what we've also done is within our software, we've added what we call a weld analysis tool. And in this application, I'll be looking at micro hardness testing of welded components. And within the tool, you pick out the weld tool, for instance. And in this case, you can specify if you want it angled whenever you're working with butt welded components, for instance, or if it's a fillet, for butt welded, it can be traditionally where you're putting your left base, put 3 indentations, and we've also put an allowance that you can add additional indentations if you want to properly evaluate your base metal. And then in the has, you can also specify how many indents you want to place. Similarly to the weld, the right has and right base. So it's a quick way of programming, and you only need to do this once. Once it's done, it's a case of placing onto the welded component, and you run your test. And also I'm saying that within the tool, we've done it 2 ways. You can either use spacing, or you can interpolate your indentation across the base metal, the has, and the weld, which is an example I'm going to illustrate in the next slide. So this illustrates a macro weld, and in this case, I've used about 10 kilos to do the impressions. And as you can see on the image where it's written ready to test, the scale bar there is 20 millimeters, so it's quite a big butt weld component, and indicates where I've placed the 3 indentation in the base metal, within the has, the weld, the right has, and back to the base metal. And if I zoom that in a little bit, you can see where the impressions are within the heat-affected zone. As illustrated there, this surface has been etched. Again, most systems or automatic systems should be able to cope with etched surfaces to be able to do hardness evaluation. And as an illustration, this shows you, once you've done the test, illustrates a match where you've got your base metal, your weld, and base metal being on equal hardness, but you do have affected zone exhibiting high hardness value as illustrated there. So potentially, if you do routine weld evaluation, these areas that should be of concern whenever working with this kind of welds. We've also looked at an overmatched component. And in this case, you can see the scale bar there is about 10 millimeters, so a little bit of a smaller butt welded component. And in this case, you can see the welded region is quite hard compared to the base metal. And then within the heat affected zone where we've put or placed the indents, you can see there's slight variation in hardness, but also equally matching the base metal, so not too bad. But the problem you may have in this case is because you've got a harder weld, potentially that could pose challenges during or in service of this component. Something else that you can also do with weld evaluation, you can map out your component or welded component, and when you map it out, it gives you an indication of a heat map for different hardness levels within a welded component. So the image I've shown you there on the top left, that is as etched component showing you the weld, the heat affected zone. So this is 3 beads. But of course, when you welded the first bead and then do the second one, each will have its corresponding heat affected zone. That's where you can see this fine-grained region there. But then when you map this out, you do get quantitative data as illustrated in the chart below for different hardness values. And in this case, we did approximately 3,000 indents. This might take a couple of hours to get. So if you're doing weld research, weld analysis, it is a tool to utilize just to make sure that whatever parameters you're using are correct. And the advantage, of course, with weld mapping as well is it gives you a qualitative indication of where potentially you've got high residual stresses due to the thermocycling during welding, and potentially where you'd have failure occurring on that material. Another illustration here, I'm showing you large butt welded components. The top images, of course, still indicates different weld passes, as you can see, the different colors. And when I mentioned the heat-affected zone being a little bit softer, you can see in this case indicating the different weld passes. And for this top weld, what is of concern is near the fusion line, the heat map shows it's considerably harder compared to the base metals on either side of the weld. And this potentially is where we say failure may occur during service along the fusion line into the house because of this high hardness or high, what we consider high residual stresses. For the micrograph for the bottom, again, another heat map. And in this case, you can see it is equally matched. So we don't have high hardness along the fusion line and near the affected zone. But in this case, because you've got the cap of the weld, which of course will be the last bit to solidify, you still have an indication of where you've got high residual stresses or high hardness level. And potentially this could be regions where you may have cracks or initiating or starting for when this component is exposed to service conditions. Another thing that I was going to talk to you about on hardness mapping. In this case, we're looking at additive manufacturing components. And additive manufacturing component, where you're using laser metal deposition, for example, LMD, it's akin to welding technique where you've got your feedstock coming in. It can be any material, titanium, austenitic steels, or copper, depending on which material you're working with. You've got your laser high heat input to melt it, and then you are layer by layer building that component up, as illustrated there on the video showing you how the process works. And at the bottom, I'm showing you an LMD process for blade repair, or when you're building a turbine blade up through an additive manufacturing process. And if you map this out, as illustrated in the image in the center there with a different heat map, in this case, the arrow pointing downwards indicating the start building, the top being the first layer, and as you build your component up into the finish point. And in this case, you're looking at a titanium component. And basically, you can hardness map that surface, and it will give you an indication where you still have high hardness that might be potentially regions for crack development. And this is why you can mitigate this in additive manufacturing by if you have a bed that is heated up, so you're always exposing your component to high temperature to minimize stress development within the component. So all in all, you can map out additive manufacturing components as well. And I remember with this one, we did again about 3,000 to 4,000 indents. Quite a large component to give you an indication of different microstructures that are occurring in your component. So I'm going to do another quick poll. And in this case, it's before we get into direct or indirect verification. And in this case, I just want to have a feel of what kind of checking do you periodically check, or internal periodic verification of your machine. So if you can quickly do the poll for me. So outrightly, I can see people doing monthly and every change of scale or indenter, but also daily checks are quite popular. So I'm going to give it a couple of more seconds. Okay. At least it gives me a breather as well to breathe before carrying on. So I've got 80% have already voted. So I'm going to close the poll for those who have not voted and show you the results. And as you can see, it's good that most of you are doing internal periodic verification with the change of scale or indenter as number one. And then daily checks are also partly there, and I would guess for those guys working with NatCap, that might be the case. But also some of you guys are doing monthly and weekly checks. So back to the presentation. So what is direct and indirect verification? So direct verification is where we are checking all the critical components separately and ensuring that that hardness tester is performing as per the standard. For example, if you're looking at VCAS for ISO 6542 version 2 or STME 92, specify that this needs to be done for new machine. And this can be performed by the manufacturer or an outside certification agencies. And for direct verification, the schedule within ISO says that you need to do this verification for the first time when you're working with your machine, or whenever you do any adjustment or modification or repairs in the machine. And if you haven't done indirect verification or for over 14 months, then direct verification of your machine should be carried out. For STM, it does specify that for a new machine, as well as whenever you're carrying out any adjustment or repairs are made, or when your machines fails the annual indirect verification, when you've got external certification agency or the manufacturer looking at your tester. For indirect, which is again, in this case, I'm referring to the annual indirect verification. This is a way of verifying that the overall performance of your testing machine using reference blocks also adheres to the ISO 6547 version 3 for vehicles. Of course, there are other standards for Brinell and Rockwell. So for indirect, it's just making sure that overall performance of your machine is okay in reference to the test blocks that you're using. And for ISO, it does specify that this needs to be performed at least once every 12 months, directly, basically after you've done direct verification. And for STM, it does say also recommended every 12 months, but not longer than 18 months. So some of you guys might be working towards ISO or STM or both techniques. And we're also saying that following a direct verification, of course, you need to do indirect verification. And to qualify an indenter that was not verified in the previous last indirect verification, you may need to do the annual indirect verification of your tester. So in this case, I'm just referring to Vickers, but the same applies for Brinell and Rockwell scales. The next is looking at what we consider as internal periodic verification. And for the internal periodic verification, you're checking and monitoring the performance of your machine using standardized test blocks. And this is, of course, is carried out more often than the annual indirect external ISO or STM verification. And you do this periodically so that you have the confidence level that the test data you've got for your hardness is okay. And for some of you guys who get audited, it is essential to ensure that this is periodically checked. And within our software, of course, we've added a tool that helps to monitor periodic verification. And in this case, you can take, for example, in this case, we're looking at 7 to 25 vehicles, and you can specify when you want the software to prompt you to do any the verification. This can either be daily or whenever you change indenter or load, or it just depends on the kind of application you're doing. And as an example here, I'm talking about the 725 vehicles HV1 test block. And this is looking at on a monthly basis. And we said with Damet, it will automatically give you this. The moment you start software, it says you need to either do every time you log into the software or start a new test method. It will ask you to verify, and this test data is automatically stored. And you can pick this up later on if somebody wants to verify your or audit your testing method, for example. And that's why we say it's a nice tool to have in any software, but we've incorporated this as a standard way of hardness testing of materials. And as a summary for indirect or internal periodic verification, for the ISO I mentioned, it says for indirect internal periodic verification, you need to do this first test of each week of every time you use a different test force, but it is recommended to do it daily. And also, whenever you change your test force, you may need to do ISO indirect internal periodic verification. And the moment you change your indenter, physically change the indenter, you do need to do the internal periodic verification. For STM, similarly, it does say that within a week prior to the machine being used, you need to do internal periodic verification. But it is recommended that each day the machine is used for NADCAP application, that this is checked. And whenever the machine is moved from one point to another, if you've got a small movement within your lab, this needs to be looked into. Also, whenever you change the indenter or the task force. And for Beulah, of course, we manufacture equipment. We do provide test blocks. We're saying, of course, adhere to the STM or ISO recommendation. And we're saying a week should be considered as a minimum way of checking using test blocks. But the optimum way, if you're doing periodic check, high volume application where you're doing a lot of hardness checks, like I remember when we did the poll, nearly 90% were doing surface and core hardness checks. So it might be necessary to do this on a daily basis. And in this case, you're looking the high load and low load, depending on which load or Vickers level you're operating to. And I've also put there as a caveat that always check respective standards, Vickers, New, Procol, and Brinell scales, to ensure that your machine is performing as it should. And that concludes this second webinar looking at hardness applications. You can log onto our website, send us an email, drop us an email if you've got any more query, questions, or in-depth information you want me to share or discuss further with you. And we've got in our website, you can get technical updates on this, tech notes. There's a lot of information available online within our website. And for sample preparation, where we mentioned about having good prep to give you good analysis, then if you get our Bueller Summit, can be a good starting point to properly prepare your samples. And that's how the Summit guide looks. So it gives you how you section, mount, grind. And we also have detailed information on hardness testing, image analysis, etching, giving you different etchings that you can use. So it is a nice book, or you can download on our website to use for your routine testing and sample preparation, also to give you guide on how you should do hardness testing as well. And that's just typical example looking at ferritic material, tells you what method to use. And I've also highlighted there for hardness testing a bit more detail that is covered on the first webinar as well, but there will be more detail on the book if you want to have a look as a reference later. I'd like to thank you for taking time out to attend the webinar. I know my colleague, Damien Crozet, has been replying to your messages. I will also latch onto them and reply to any queries or questions you still have in the chat window. But like I mentioned before, you can send us an email at tech@Bueller Support, and we should be able to pick up any queries that you may have. Thank you for attending, and I hope it's been an interesting and beneficial webinar for you. So at the end of this, you'll have a survey question that will ask you a couple of questions. The recording of this webinar will be available for download as well. You can get it and go through it as well at your pleasure. Thanks for joining us, and goodbye.